points opposite to this one points opposite to that one. And on the negative phase, they point in the direction of the coordinate system. And this one is called S what? S X Y. To me, it's not a big deal that you know very well what is the direction of the shear stress, but it is a big deal that you know what is a compression, what is a tension, and what these cross indices mean. If it is the same index, it's a normal force. If they are the indices are not the same, this is a shear stress. Normal stress, shear stress.
So how did you pick your convention of what side you wanted to be like the positive side? Because it could have easily been the left side, right? Like,
well, yes, you could do that, but people before me agreed on this and said that this is going to be positive. So I'm just following what other people agreed on before. Actually, this convention is used in geomechanics, but if you were to work on just the mechanics, like for example metals, they use the opposite because they are more interested in tensile failure rather than in compression failure. And in our case, in rocks, we mostly have compression rather than tension. So they use the opposite. But in geomechanics, we use this one. So you just have to complete this one, and I would also try to figure this in 3 dimensions. It's not a lot more difficult than this, but if you know this in 2 dimensions, in 3 dimensions, just one step more. Okay? All right. So, any questions about this problem? No? Let's talk about the homework, the problem which is due today. Okay, so in problem number 3, you have something like this. You have water, you have the seafloor, there is a region which is sandy, and there is another region which is clay and sand. With the data that you have, you have a density of water which is not constant, so you have to use that in order to compute the stress at each step, but it's not constant. And after a certain point, I'm asking you to consider it constant, equal to 1031 density of water. And then you have the density, the bulk density over here, which starts at the seafloor, and also that one is not constant, right? So you have to use that data in order to compute the total vertical stress. So that's the first thing that you're going to compute, the total vertical stress. But in order to do that, you need to know what is the pore pressure or the fluid pressure at the seafloor, okay? So, for sure, if we just have water, we're gonna have hydrostatic pore pressure. So up to here, after we don't know, okay? But up to here, for sure, the pore pressure is going to be hydrostatic. When you get to that point, your first point of vertical stress is going to be that one. So now you start adding the weight of the entire layers, considering also the sediments in it. So you're gonna get something which is like this. That's a vertical stress, okay? And after you get that, then I'm telling you that we do not know what is pore pressure. So, one, I'm asking you to make a hypothesis saying that it is hydrostatic. We actually don't know what it is. No? But let's assume it is hydrostatic. And I am asking you to compute that hydrostatic pore pressure, which will be this one. But we don't know if that's real or not, okay? And second, you have to use a shell porosity in order to compute the actual pore pressure. And with that shell pore pressure, shell porosity, you will be able to calculate what is the effective stress, and from that effective stress, you will be able to calculate the pore pressure, and you will see that actually this is something like this. It gives you points that will line up like the ones I did in this schematic. Yes?
Okay, so whenever we do the actual pore pressure, do you want us to extrapolate a hypothetical line to the first point?
Well, let me finish with this. So now I know that for sure this one, it's more or less like this. And that data finishes in there, right? So since that one kind of approaches the hydrostatic pore pressure, it makes a lot of sense to think that above that point is hydrostatic, and whenever that pore pressure departs from hydrostatic is when we get overpressure. Remember, the parameter of overpressure, lambda p, is going to be always less than 1. It's just when it approaches 1 that you get overpressure.
Professor, could you zoom out a bit?
Yes. So that's all you have to do. And in most of these plots, we do not plot effective stress, because effective stress, we can see it is right there. So you don't have to plot it. It's what you see over there. Or you can plot it in a separate plot. Okay, guys, we have 5 minutes left, and I want to talk about the last problem, okay? So the last problem, this is a simplification of the data that you have, okay? This is a place onshore in the coast of Louisiana, and we have two files. We have the LAS file, and we have the deviation file, okay? If you open the deviation file, or let's go first to the LAS file. Okay. So here you see it tells you when the log starts, when it ends. You shouldn't expect to have any data before that point and after that point. And here also tells you what is the elevation of the Kelly bushing in feet. So it's 36 feet, okay? So what does that mean? It means that your Kelly bushing here, it is 36 feet above the sea level. So if this were the rig over here and this is the water, it will be somewhere over there. Okay? You don't need to use this yet. but you know, that's what the data is telling you. You start to measure depth from here, right? A measure depth can go like this. It's not the vertical line. All right, so let me come back over here. If you really want to get this done the way it will be done in an actual job, you should open this LAS file, okay? But if you don't want to do that right now, I'm giving you another option, which is instead of opening this LAS file, which is a regular file for well logging files, and that's something you're going to use in senior design too, very likely. You have this other file, which comes from the LAS file, and it gives you measure depth, compression velocity, shear velocity, well actually slowness, and bulk density. It starts at this depth and it ends at 7,000 something. These values, negative 999, that means that there is no data, okay? So don't pay attention to those, that means no data. But if you go down, you will see that at some point you start to see actual data, at least for the bulk density. And if you go down more, now we have compression velocity and bulk density. And if you go deep enough, now you have depth, measured depth, compression velocity, shear, and bulk density. So now you have measured depth and you have density. But you cannot compute stress with measured depth. You need true depth, okay? Yes, you have a question?
So, are you saying that we should disregard the ones that had a negative 999?
Yes. So, whenever you have this negative 9999, and also for depths which are above this depth, I am asking you over here to assume, if I remember correctly, a density of 2 grams per centimeter cube. Okay? Just assume that constant above that depth, because you don't have any data. You have to do some assumption. And that's a reasonable assumption for that depth. Okay. Notice that here we have measured depth and we have bulk density. This one kind of looks similar to what we have here, right? Actually, this column, this one is depth, this is density. But in this case, this one is true vertical depth, and this one is density. So the additional step that you have to do in this case is once you open this in Excel, here you need another column, which is going to be true vertical depth, okay? And you're gonna get that one from the deviation file that also you're gonna open in Excel the same way that you open the other ones, and it tells you here a few columns about the name of the well, I think this is the API number, and the first column is measure depth, second one is TVD, and then you have east-west offset, north-south offset, and true vertical depth sub C. Let me tell you what that is. Okay, in that file you have measure depth, you have true vertical depth, and also you have true vertical depth sub C. In this case, the difference between true vertical depth and true vertical depth sub C is very small, because this is near the shore. So either use TVD or TVDSS. It's going to give you a very similar value, okay? Ideally, you should use TVD sub C. But if you use just TVD, it's also going to be fine. Your number is not going to change. But finally, you're going to get a column of measured depth. Then you're going to do a correlation between measured depth and true vertical depth, and you will be able to fill this one, and here you're gonna have the bulk that you know from measure depth, and here you have SV. SV is calculated with these two columns, not with that one, with these two. So the delta Z comes from here, and the average density comes from that one. Okay? All right, guys. Try to solve it and submit your homework before midnight, okay? Have a good weekend, guys. Take care.